Beneath the rust-colored surface of Mars, hidden for billions of years, ancient rivers of molten rock once carved a fiery underworld, flowing not like water, but like liquid fire, carving channels through the planet's crust. This isn't just geological oddity, it's a revelation. These magma rivers, now frozen in silence, suggest Mars wasn't always the dry, dead world we see today. Instead, it may have pulsed with volcanic activity, its interior churning like a simmering cauldron. The discovery challenges our assumptions about planetary habitability. If Mars, once thought a frozen wasteland, had a dynamic, molten plumbing system, maybe other rocky exoplanets, previously deemed inhospitable, could harbor similar secrets. Imagine a world where underground oceans of magma mingled with subsurface water, creating conditions ripe for life. This finding doesn't just rewrite Mars' history, it expands the very definition of what makes a planet capable of sustaining life, turning our search for habitable worlds into something far more thrilling. In the vast expanse of the solar system, Mars has long been a subject of fascination. While we know it's a cold, barren world today, new research suggests it may have once been far more dynamic. Scientists have discovered compelling evidence that rivers of molten rock, or magma, once flowed beneath the Martian crust billions of years ago. This finding challenges our understanding of the planet's geological history and raises exciting questions about the potential for life on other rocky worlds. But how did researchers arrive at this conclusion, and what does it mean for the search for habitable planets beyond Earth? Let's explore what this discovery reveals about Mars and its implications for the broader universe. The idea that Mars once harbored magma rivers is rooted in a careful analysis of the planet's geological features. By studying the distribution of certain minerals and the patterns of ancient lava flows, scientists have pieced together a picture of a Mars that was geologically active in its distant past. These magma rivers, much like their terrestrial counterparts, would have been vast networks of molten rock that carved their way through the crust. However, unlike Earth's rivers, which are sustained by liquid water, these Martian rivers would have been driven by the planet's internal heat. The presence of such features suggests that Mars had a more active interior than previously thought, with a mantle that generated significant thermal energy. One of the key clues pointing to these ancient magma rivers lies in the composition of Martian rocks. Certain minerals, such as pyroxene and olivine, are commonly found in volcanic regions on Earth and are indicative of magma activity. By analyzing the abundance and distribution of these minerals across the Martian surface, researchers have identified regions that align with what would be expected if magma had once flowed beneath the crust. Additionally, the presence of certain types of lava flows, those that suggest a high volume of molten rock, further supports the hypothesis. These findings are not just theoretical, they are based on data collected by spacecraft like NASA's Mars Reconnaissance Orbiter and the Mars Express mission, which have provided detailed images and spectroscopic data of the planet's surface. But how did these magma rivers form, and what role did they play in shaping Mars' early history? The answer lies in the planet's internal structure and the processes that govern planetary evolution. Like Earth, Mars is believed to have had a molten interior in its early years, with heat generated by radioactive decay and the planet's own gravitational compression. This heat would have driven convection currents within the mantle, creating the conditions necessary for magma to rise toward the surface. However, unlike Earth, which has a dynamic plate tectonic system that continuously reshapes its crust, Mars is thought to have lost its plate tectonics billions of years ago. This means that the planet's geological activity was likely more episodic, with periods of intense volcanic activity followed by long periods of dormancy. The discovery of magma rivers on Mars adds a new layer to this story. It suggests that the planet's early geological activity was not only more intense but also more widespread than previously assumed. These rivers would have been capable of transporting heat from the interior to the surface, potentially influencing the planet's climate and even contributing to the formation of liquid water. While Mars is now a dry world, evidence from ancient river valleys and lakebeds indicates that it may have had a warmer, wetter climate in its distant past. The presence of magma rivers could have played a role in maintaining this climate by releasing heat and gases into the atmosphere, creating conditions that might have supported microbial life. This finding has significant implications for our understanding of planetary habitability. For decades, scientists have focused on identifying planets that are similar to Earth in terms of size, composition, and atmospheric conditions. However, the discovery of magma rivers on Mars suggests that habitable environments can arise in a broader range of planetary conditions. If a planet like Mars, with a thin atmosphere and cold surface today, could have once hosted magma-driven processes that supported liquid water, then other rocky planets in the galaxy might have similar potential. This expands the criteria for identifying potentially habitable worlds, encouraging astronomers to look beyond the traditional Earth-like model. The research also raises intriguing questions about the geological evolution of Mars and its relationship to Earth. While both planets are rocky and have similar compositions, their geological histories have diverged significantly. Earth's active plate tectonics has allowed for continuous recycling of the crust and the regulation of atmospheric gases, whereas Mars' lack of plate tectonics has led to a more static surface. The presence of magma rivers suggests that Mars may have had a more active geological past, with processes that could have sustained a more dynamic environment for a longer period. This challenges the assumption that plate tectonics is a prerequisite for planetary habitability and opens new avenues for studying the diversity of planetary systems. Moreover, the study of Mars' magma rivers could provide insights into the formation and evolution of other rocky planets in the solar system and beyond. By comparing the geological features of Mars with those of planets like Venus and Mercury, scientists can better understand the range of possible planetary outcomes. For example, Venus is known for its extreme volcanic activity, while Mercury has a heavily cratered surface with minimal volcanic features. The presence of magma rivers on Mars suggests that the planet's geological activity was intermediate between these extremes, offering a unique case study in planetary evolution. Such comparisons can help refine models of how planets form, cool, and change over time, shedding light on the processes that shape the habitability of exoplanets. The implications of this research extend beyond planetary science, touching on broader questions about the potential for life in the universe. If Mars, with its cold and barren surface today, could have once hosted conditions that might have supported life, then other planets with similar histories might also have had the potential. This finding encourages scientists to look for signs of ancient geological activity on exoplanets, such as evidence of volcanic features or mineral compositions indicative of magma flows. By doing so, we can expand our search for habitable worlds and increase the chances of discovering planets that may have once harbored life. In conclusion, the discovery of magma rivers beneath Mars' crust represents a significant breakthrough in our understanding of the planet's geological past and its potential to support life. This finding not only enriches our knowledge of Mars but also broadens the scope of what we consider habitable planets. As we continue to explore the cosmos, the lessons learned from Mars will undoubtedly play a crucial role in shaping our search for life beyond Earth. The story of Mars' ancient magma rivers is not just about a distant world, it's a reminder of the dynamic and diverse processes that shape planets across the universe, and the possibilities they may hold for life. For decades, scientists have peered at Mars through telescopes and spacecraft cameras, searching for clues about its ancient past. But the idea that rivers of molten rock once flowed beneath its surface, like rivers of water on Earth, was once considered speculative. Yet recent research, built on decades of data from Mars missions, has revealed a startling possibility that magma, the molten rock that powers Earth's geology, may have carved vast networks beneath the red planet's crust. This discovery isn't just rewriting Mars' history, it's reshaping our understanding of which rocky worlds could have harbored conditions suitable for life. To grasp how scientists arrived at this conclusion, we need to follow the trail of instruments, observations, and analysis that turned a long-held hypothesis into a plausible reality. The journey begins with the Mars Reconnaissance Orbiter, a spacecraft that has been orbiting the planet since 2006. Equipped with a high-resolution camera and a spectrometer, it has mapped the Martian surface in exquisite detail, capturing features that hint at a dynamic geological past. Among these features are vast networks of channels, some stretching hundreds of kilometers, that bear an uncanny resemblance to river systems on Earth. But these aren't carved by water, they're shaped by something else entirely. The channels are too wide, too deep, and their patterns suggest a different kind of fluid, one that flows under immense pressure and heat. These observations, combined with data from earlier missions like the Viking orbiters in the 1970s, hinted at a hidden world beneath the Martian surface, one where magma might have once moved through the crust like a subterranean river. To confirm this, scientists turned to a different kind of tool, thermal imaging. The Mars Odyssey orbiter, which has been in orbit since 2001, carries an instrument called the Thermal Emission Imaging System, or THEMIS. This device measures the heat radiating from the Martian surface, allowing researchers to map temperature variations across the planet. When they analyzed the data, they noticed something intriguing. Certain regions, particularly in the Tharsis and Elysium plateaus, areas known for their massive volcanoes, showed unusually high heat signatures. These readings didn't match the expected thermal properties of solid rock. Instead, they suggested the presence of subsurface magma chambers or flowing lava. But how could they be sure these weren't just residual heat from ancient volcanic activity? The answer lay in a deeper dive into the planet's geological history. By studying the distribution of volcanic features, scientists began to piece together a picture of Mars' past. The Tharsis region, for example, is home to the largest volcano in the solar system, Olympus Mons. But this isn't just a single mountain, it's part of a vast volcanic province that suggests widespread magma movement in the planet's early history. The presence of lava tubes, which are hollow tunnels formed by flowing lava, further supported the idea that magma once moved through the crust. These tubes, some of which stretch for hundreds of kilometers, could have acted as natural conduits for molten rock, much like rivers do for water. However, the key to confirming this hypothesis required a more direct approach. Enter the InSight lander, which touched down on Mars in 2018. Unlike previous missions, InSight was designed to study the planet's interior. Its primary instrument, the Seismic Experiment for Interior Structure, or SEIS, is a seismometer that detects vibrations beneath the surface. While InSight's main goal was to measure Marsquakes, the data it collected also provided valuable insights into the planet's internal structure. By analyzing the way seismic waves travel through the crust and mantle, scientists could infer the presence of magma-filled channels or reservoirs. The results were striking. The seismic data suggested that Mars' crust is thinner in certain regions, allowing magma to flow more freely. This thinning, combined with the high heat signatures observed by THEMIS, pointed to a subsurface network of magma that could have once been active. But how did these findings connect to the idea of rivers of magma? The answer lies in the interplay between heat, pressure, and the planet's geological evolution. Mars, like Earth, has a molten core, but its crust is much thinner and less dense. This means that magma could have risen more easily through the crust, creating channels that allowed it to flow across vast distances. The key to understanding this process is the concept of mantle plumes, columns of hot material that rise from the planet's interior. On Earth, these plumes are responsible for volcanic activity, but on Mars, they may have played a different role. By studying the distribution of volcanic features and the thermal data, scientists proposed that these plumes could have generated the heat needed to sustain magma rivers beneath the surface. To test this theory, researchers turned to computer simulations. Using data from Mars missions, they modeled the planet's geological history, simulating how magma might have flowed through the crust. These models revealed that if Mars had a sufficiently active mantle, the heat generated by volcanic activity could have created a network of magma channels, much like the rivers of water that once carved the planet's surface. The simulations also suggested that these magma rivers could have persisted for millions of years, providing a stable source of heat and potentially even water vapor, which could have contributed to the formation of liquid water on the surface. This connection between magma activity and the potential for habitable conditions is what makes the discovery so significant. The implications of this research extend far beyond Mars. If rivers of magma once flowed beneath the red planet's crust, it suggests that similar processes may have occurred on other rocky exoplanets. The discovery challenges the traditional view that habitable worlds must have liquid water on their surfaces. Instead, it opens the door to considering planets where subsurface geothermal activity could have created environments conducive to life. This shift in perspective is particularly relevant as astronomers search for habitable worlds beyond our solar system. By understanding how Mars' interior once functioned, scientists can better assess the potential for life on other planets with similar geological histories. Yet, the journey to confirm this hypothesis wasn't without its challenges. Early data from Mars missions suggested the presence of volcanic features, but the idea of active magma rivers beneath the crust was met with skepticism. Scientists had to rule out alternative explanations, such as residual heat from ancient volcanic eruptions or the presence of subsurface water. The breakthrough came when researchers combined multiple lines of evidence: thermal imaging, seismic data, and geological modeling. Each piece of the puzzle reinforced the others, creating a compelling case for the existence of magma rivers beneath Mars' surface. One of the most intriguing aspects of this research is its connection to the broader question of planetary evolution. Mars, once a potentially habitable world, now has a cold, dry surface. But the presence of magma rivers suggests that the planet may have had a more dynamic interior in its early history. This dynamic interior could have influenced the planet's climate, atmosphere, and even its magnetic field. By studying these processes, scientists gain insight into how planets evolve over time, and how their internal activity shapes their potential to support life. As the research continues, new missions are set to explore Mars in even greater detail. The Perseverance rover, for example, is equipped with instruments that can analyze the chemical composition of rocks and soil, providing further clues about the planet's geological history. Future missions may even include drilling into the crust to search for evidence of ancient magma activity. These efforts will build on the foundation laid by previous missions, refining our understanding of Mars and expanding the possibilities for life on other worlds. In the end, the discovery of magma rivers beneath Mars' crust is more than just a revelation about the red planet. It's a testament to the power of scientific inquiry and the ingenuity of researchers who have spent decades peering at Mars through telescopes and spacecraft. By piecing together data from multiple missions, they've uncovered a hidden world of molten rock and heat, challenging our assumptions about what makes a planet habitable. As we continue to explore the cosmos, this finding reminds us that the search for life beyond Earth is as much about understanding the processes that shape planets as it is about finding water or oxygen. The story of Mars' magma rivers is just one chapter in a much larger narrative, one that could redefine our understanding of life and the universe. Imagine a world beneath the surface of Mars, hidden from view, where rivers of molten rock once flowed like liquid veins through the planet's crust. This is not science fiction, it's the revelation of a groundbreaking study suggesting that Mars, long thought to be a cold and barren world, may have once harbored a dynamic, geologically active interior. These rivers of magma, flowing beneath the Martian surface, are more than just a curiosity, they represent a profound shift in our understanding of planetary habitability. For decades, scientists have debated whether Mars could have supported life, but this discovery adds a new layer to the puzzle, hinting that the conditions necessary for life might be more common in the universe than we ever imagined. Let's explore how this finding reshapes our view of the cosmos and what it means for the search for life beyond Earth. To understand the significance of these magma rivers, we must first grasp the nature of planetary geology. On Earth, magma is the molten rock that fuels volcanic activity, shaping our planet's surface through eruptions and the formation of mountain ranges. But what if Mars, too, once had a similar system? The presence of magma rivers suggests that Mars was not a static, lifeless world but a planet with a complex internal structure, capable of generating heat and movement. This heat would have driven geological processes, much like Earth's, creating conditions that could have supported life. But how did scientists arrive at this conclusion? By studying the geological features of Mars, researchers have pieced together a story of a planet that was once far more active than previously believed. The key lies in the planet's crust. The Martian crust, like Earth's, is a rigid layer that sits atop a more malleable interior. However, unlike Earth, Mars lacks a global magnetic field and has a much thinner atmosphere, making it a harsher environment. Yet, the presence of magma rivers implies that Mars once had a more active interior, with heat escaping through the crust in ways that could have sustained geological processes. One of the most compelling pieces of evidence comes from the analysis of Martian rock formations. Certain features, such as layered deposits and volcanic structures, resemble those found on Earth in regions where magma has interacted with the crust. These similarities suggest that Mars may have once had a system of magma channels, much like the rivers of molten rock that once flowed beneath Earth's surface. But why does this matter? The answer lies in the connection between geological activity and the potential for life. Life as we know it requires liquid water, a stable temperature range, and a source of energy. While Mars is now a dry, cold world, the presence of magma rivers indicates that it may have once had the conditions necessary to support these essential elements. Magma, when it interacts with water or other volatile compounds, can generate heat and create hydrothermal systems, environments where life might have thrived. On Earth, hydrothermal vents on the ocean floor are known to host complex ecosystems, thriving in the absence of sunlight. If Mars once had similar systems, it could have provided a refuge for microbial life, even in its early, harsher days. This discovery also challenges our assumptions about what makes a planet habitable. For years, the search for life beyond Earth has focused on planets with atmospheres similar to Earth's, capable of retaining heat and protecting against cosmic radiation. But the presence of magma rivers on Mars suggests that habitability might be more flexible than we thought. A planet doesn't need a thick atmosphere or a strong magnetic field to support life, it might simply need a dynamic interior capable of generating heat and creating the right conditions for liquid water. This expands the range of planets we should consider when searching for life, including many rocky exoplanets that were previously deemed too inhospitable. To put this in perspective, let's compare Mars to Earth. Earth's geology is driven by a combination of internal heat and the planet's rotation, which generates a magnetic field that shields the atmosphere from solar radiation. Mars, however, lacks this magnetic protection, leaving its surface exposed to harsh cosmic rays. Yet, the presence of magma rivers suggests that Mars once had a more active interior, with heat escaping in ways that could have sustained geological processes. This internal activity might have been enough to create pockets of warmth and water, even in the absence of a protective atmosphere. It's a reminder that planets can have diverse ways of maintaining the conditions necessary for life, and that our understanding of habitability must evolve to account for these possibilities. The implications of this research extend far beyond Mars. If a planet as seemingly inhospitable as Mars could have once harbored magma rivers and the potential for life, what does that mean for other rocky planets in our galaxy? The universe is filled with exoplanets, planets orbiting stars other than our Sun, that are similar in size and composition to Earth. Many of these worlds are in the so-called habitable zone, where temperatures could allow liquid water to exist on their surfaces. However, the presence of magma rivers on Mars suggests that even planets outside this zone might have had the internal processes needed to support life. This broadens the scope of our search, encouraging scientists to look for signs of geological activity in addition to atmospheric conditions. But how do we know that Mars once had magma rivers? The answer lies in the study of planetary geology and the analysis of Martian rock formations. Researchers have used data from orbiters and landers to map the surface of Mars, looking for features that could indicate past geological activity. One of the most striking findings is the presence of what appear to be ancient lava tubes, cavernous structures formed when molten rock flows beneath the surface and then solidifies. These tubes, if they once contained flowing magma, would have been similar to the lava tubes found on Earth, which are known to host unique ecosystems. The existence of such structures on Mars provides strong evidence that the planet once had a system of magma channels, capable of sustaining long-term geological activity. Another clue comes from the study of Martian minerals. Certain types of minerals, such as those formed by hydrothermal processes, are often found in regions where magma has interacted with water. These minerals are also common in Earth's volcanic regions, where they form in the presence of both heat and liquid water. The presence of these minerals on Mars suggests that the planet may have once had environments where water and magma coexisted, creating the conditions necessary for life. This is a crucial point because it shows that Mars was not just a dry, cold world, it was a planet with the potential for complex chemical interactions that could have supported microbial life. Of course, the question remains, if Mars once had magma rivers, what happened to them? The answer lies in the planet's evolution. Over billions of years, Mars' internal heat has gradually diminished, leading to the cooling of its interior and the cessation of geological activity. The absence of a magnetic field has also contributed to the loss of its atmosphere, leaving the surface exposed to the harsh conditions of space. But the fact that Mars once had the conditions necessary for life means that it was, for a time, a viable candidate for hosting microbial ecosystems. This is a powerful reminder that planets can undergo dramatic changes over time, and that the potential for life may have existed in ways we are only beginning to understand. This discovery also raises new questions about the role of geological activity in the development of life. On Earth, the movement of tectonic plates and the presence of volcanic activity have played a crucial role in shaping the planet's environment, influencing climate patterns and creating the conditions necessary for life to thrive. If Mars once had a similar system, it could have provided the same kind of dynamic environment that supported life on Earth. This suggests that the processes that made Earth habitable might be more common in the universe than we previously believed, and that the search for life should consider not just atmospheric conditions, but also the internal processes of a planet. In the broader context of astrobiology, this finding challenges the traditional view of habitability. For years, scientists have focused on planets with atmospheres capable of retaining heat and protecting against radiation, but the presence of magma rivers on Mars shows that life could have emerged in a variety of environments. This is a significant shift in perspective, one that could lead to new discoveries in the search for life beyond Earth. By expanding our understanding of what makes a planet habitable, we open the door to exploring a wider range of worlds, each with its own unique combination of geological and atmospheric conditions. The implications of this research are far-reaching. It not only changes how we view Mars but also how we approach the search for life in the universe. If a planet as seemingly inhospitable as Mars could have once supported geological processes that might have created the conditions for life, what other planets might have done the same? This is a question that will drive future research, as scientists continue to explore the vast expanse of our galaxy in search of signs of life. The discovery of magma rivers beneath Mars' crust is more than just a scientific curiosity, it's a reminder that the universe is full of possibilities, and that our understanding of life's potential is still in its early stages. As we look to the future, this finding serves as a catalyst for new exploration and discovery. Missions to Mars and other rocky planets will need to consider the possibility of past geological activity, searching for signs of magma rivers, hydrothermal systems, and other indicators of a dynamic interior. These missions could provide further insights into the history of planetary evolution and the conditions that might have supported life. By expanding our search beyond the traditional criteria for habitability, we increase our chances of finding evidence of life elsewhere in the universe. In the end, the discovery of magma rivers beneath Mars' crust is a testament to the complexity and diversity of planetary systems. It reminds us that the universe is not a place where life is confined to a few familiar conditions, but a vast, dynamic realm where the potential for life exists in many forms. As we continue to explore the cosmos, we must remain open to the possibility that life may have taken root in places we never imagined, hidden beneath the surfaces of distant worlds. The search for life beyond Earth is not just about finding water or air, it's about understanding the intricate processes that shape planets and the conditions that make them capable of supporting life. And in doing so, we may one day uncover the truth of whether we are truly alone in the universe. For decades, the search for life beyond Earth has centered on the question of water. Mars, the red planet, has long been a prime candidate. Early missions in the 1960s and 1970s, like NASA's Mariner 4 and Viking landers, revealed a barren landscape of dust and rock, but also hinted at a more complex past. The Viking orbiters captured images of vast valleys and channels, suggesting that liquid water may have once carved these features. These findings sparked a decades-long quest to uncover Mars' ancient history, leading to a series of missions that gradually painted a picture of a world once teeming with water and possibly even life. Yet, the story of Mars' habitability has never been straightforward. While water is essential for life as we know it, its presence alone doesn't guarantee the conditions needed for life to thrive. Over time, scientists have realized that other factors, like heat, chemistry, and the presence of certain minerals, also play critical roles. This brings us to a groundbreaking discovery, evidence suggesting that rivers of magma once flowed beneath Mars' surface, a finding that could reshape our understanding of which planets might have supported life. To grasp the significance of this revelation, we need to look back at how our knowledge of Mars evolved, starting with the earliest missions that hinted at a wetter past, through the discoveries that revealed the planet's volcanic history, and finally to the recent research that links these two elements, water and magma, as potential keys to habitability. The story begins in the 1960s, when the first close-up images of Mars challenged our assumptions about the planet. The Mariner 4 flyby in 1965 showed a surface covered in craters, leading many to believe Mars was a desolate world. But the Viking missions of the 1970s changed that narrative. The Viking orbiters captured high-resolution images of sprawling valleys and river-like channels, suggesting that liquid water had once carved these features. These observations were met with skepticism, as the thin Martian atmosphere seemed incapable of sustaining liquid water for long periods. Yet, the data persisted, and by the 1980s, scientists began to consider the possibility that Mars had once had a warmer, wetter climate. This idea gained momentum with the arrival of the Mars Global Surveyor in the 1990s. This orbiter provided unprecedented detail, revealing features like the immense Valles Marineris Canyon system, a network of valleys and ridges that could have been shaped by ancient rivers. The spacecraft also detected layered deposits in the polar regions, which some researchers interpreted as evidence of ancient lakes or seas. These findings, combined with data from the Mars Pathfinder mission in 1997, which found mineral deposits that could only form in the presence of water, solidified the idea that Mars had once harbored liquid water. However, the story of Mars' habitability didn't end with water. Scientists soon realized that water alone wasn't enough to sustain life. The presence of heat, chemical energy, and the right combination of elements were also necessary. This led to a renewed focus on Mars' volcanic activity, a subject that had been studied for decades. Mars is home to the largest volcanoes in the solar system, including Olympus Mons, a shield volcano that towers over 22 kilometers high. These structures suggest that Mars was once geologically active, with extensive volcanic eruptions that could have released heat and gases into the atmosphere. Early studies of these volcanoes focused on their size and structure, but it wasn't until the 2000s that researchers began to explore their role in shaping Mars' environment. Missions like the Mars exploration rovers Spirit and Opportunity provided crucial insights. Opportunity, for example, discovered hematite, a mineral that typically forms in the presence of water, and found evidence of ancient water flows in the form of mineral deposits and layered rock formations. These findings reinforced the idea that Mars had a dynamic geological past, one that could have supported the chemical processes needed for life. But even as scientists pieced together Mars' history, questions remained. How did the planet's volcanic activity interact with its water systems? Did heat from volcanic eruptions help sustain liquid water for longer periods, or did it contribute to the planet's eventual cooling and drying? These questions led to a deeper investigation into the planet's internal structure and thermal history. In the 2010s, the Curiosity rover's arrival on Mars marked a new era in planetary science. Equipped with advanced instruments, Curiosity analyzed the composition of Martian soil and rock, revealing the presence of organic molecules and clay minerals, both of which are indicators of past water activity. These discoveries suggested that Mars may have had a habitable environment for billions of years, long after its surface became cold and dry. Yet, the search for habitability wasn't limited to surface features. Scientists began to consider the possibility that life could have existed underground, where temperatures and pressures might have been more favorable. This led to renewed interest in the planet's subsurface processes, including the role of magma. Magma, molten rock beneath a planet's crust, is a key driver of geological activity. On Earth, magma can create hydrothermal vents, which provide energy and nutrients for ecosystems in the deep ocean. Could something similar have occurred on Mars? The idea that magma might have played a role in sustaining life on Mars gained traction in the 2010s, as researchers examined data from seismic surveys and heat flow measurements. These studies suggested that Mars may have had a more active interior than previously thought, with regions of molten rock potentially existing beneath the surface. However, the connection between magma and habitability wasn't immediately clear. Scientists needed to understand how magma could interact with water or other chemical processes to create conditions suitable for life. This led to a series of theoretical models and simulations, which explored scenarios where magma-driven hydrothermal systems could have existed on Mars. These models suggested that if magma had once flowed through the crust, it could have generated heat and chemical reactions that sustained subsurface environments. Such environments might have provided the energy needed for microbial life, even in the absence of liquid water on the surface. The recent research that suggests rivers of magma once flowed beneath Mars' crust builds on these earlier studies. By analyzing seismic data and heat flow patterns, scientists have found evidence that Mars may have had a more dynamic interior than previously believed. These findings challenge the long-held assumption that Mars' volcanic activity ceased billions of years ago. Instead, they suggest that the planet may have experienced periods of intense geological activity, with magma rivers carving paths through the crust. This discovery has significant implications for our understanding of planetary habitability. If Mars once had magma-driven systems that could sustain life, then other rocky planets, like those in the TRAPPIST-1 system or exoplanets in the habitable zone, might also have had similar conditions. The presence of magma beneath a planet's surface could mean that even if a planet's surface is cold and dry, its interior might still be active enough to support life. This expands the list of potential habitable worlds, encouraging scientists to look beyond surface features and consider the role of internal heat and geological processes. The journey to this discovery has been shaped by decades of exploration and scientific curiosity. From the early Viking missions that hinted at a wetter Mars to the Curiosity rover's findings that revealed a planet with a complex geological history, each step has brought us closer to understanding the full story of Mars. Now, with the possibility of magma rivers beneath the Martian crust, we're faced with a new question: how did these ancient processes shape the planet's potential to support life? The answer may lie in the interplay between water, heat, and chemistry, a combination that could have created environments where life could have taken root, even in the absence of liquid water on the surface. As we continue to explore Mars and other rocky planets, the lessons learned from this research will guide our search for life beyond Earth, reminding us that the key to habitability may lie not just in the presence of water, but in the dynamic processes that sustain it. The discovery that rivers of magma once flowed beneath Mars' crust has sparked a wave of scientific curiosity, but it also raises more questions than it answers. While the research suggests that such magma rivers existed, the exact mechanisms that created them, their duration, and their role in shaping Mars geology remain uncertain. Scientists are still debating whether these features are unique to Mars or part of a broader pattern of planetary activity. For instance, the study relied on seismic data and geological models to infer the presence of magma rivers, but how confident can we be that these interpretations are accurate? Could the same features have been formed by other processes, such as water-driven activity or volcanic eruptions? These uncertainties highlight the complexity of interpreting planetary data, especially when dealing with ancient surfaces where direct evidence is scarce. The debate is not just about Mars, it's about how we understand the geological histories of rocky planets in our solar system and beyond. If Mars once harbored such dynamic processes, what does that say about the potential for similar activity on other exoplanets? And if those planets could have had magma rivers, does that expand the possibilities for habitable environments? These are the questions that continue to drive research, even as the findings challenge our assumptions about planetary evolution. The implications are profound. If magma rivers were once a common feature of rocky planets, it could mean that the conditions necessary for life, such as hydrothermal activity, chemical gradients, and heat sources, might be more widespread than previously thought. However, this line of thinking is not without its skeptics. Some scientists argue that the presence of magma rivers alone does not guarantee habitability. For life to emerge, there must be more than just heat and molten rock. There needs to be a way for energy to be transferred to the surface, perhaps through interactions with water or other volatile compounds. The challenge lies in determining whether these magma systems were sustained long enough to support such processes or if they were brief, isolated events. Moreover, the study's findings are still being scrutinized by the scientific community. While the research is intriguing, it is not yet definitive. Other researchers are questioning the assumptions made about the planet's internal structure and the methods used to interpret seismic data. Without more direct evidence, such as samples from Mars' crust or higher resolution imaging, these questions may remain unresolved for years. This uncertainty is part of what makes the topic so compelling. It reminds us that even in the face of groundbreaking discoveries, science is an ongoing process of exploration and refinement. The search for habitable worlds is not just about finding planets with the right size, temperature, or atmospheric conditions. It's also about understanding the complex interplay of geological and chemical processes that could create environments where life might take root. The idea that magma rivers once flowed beneath Mars' crust adds another layer to this search, suggesting that the potential for habitable conditions might be more diverse than we once imagined. Yet, it also underscores the importance of caution. Just because a planet has the potential for such processes does not mean that life actually emerged there. The presence of magma rivers is a necessary but not sufficient condition for habitability. This brings us to another key debate: how do we define habitability in the first place? The traditional criteria, such as liquid water, a stable temperature range, and the presence of essential chemical elements, have been expanded in recent years to include factors like geothermal activity and the availability of energy sources. If magma rivers are considered a viable energy source, then the search for habitable planets must include a broader range of geological features. However, this expansion of criteria also raises new questions. For example, how do we determine whether a planet's geology is dynamic enough to support such processes? And how do we distinguish between planets that have the potential for habitable conditions and those that do not? These are not just theoretical concerns, they have real implications for the way we prioritize targets in the search for extraterrestrial life. The study of Mars magma rivers is part of a larger effort to understand the geological histories of rocky planets. By examining how Mars evolved, we can gain insights into the processes that shape other planets, including those in distant star systems. Yet, the more we learn, the more we realize how much remains unknown. For instance, while the research suggests that magma rivers existed in the past, it does not address whether they were widespread or localized. Were these rivers confined to specific regions, or did they flow across large portions of the planet? The answer could have significant implications for how we model planetary evolution. If magma rivers were a common feature, it might indicate that Mars had a more active interior than previously thought. Conversely, if they were rare, it could suggest that the planet's geological activity was more limited. These questions are not just about Mars, they are about the fundamental processes that govern the formation and evolution of rocky planets. The debate over the presence of magma rivers also touches on the broader question of how planets lose their internal heat. On Earth, plate tectonics plays a crucial role in distributing heat and recycling materials, but Mars lacks this mechanism. If magma rivers were a way for Mars to release internal heat, it could explain some of the planet's geological features, such as its vast volcanic plains and the presence of ancient lava flows. However, the exact role of these rivers in Mars' thermal evolution is still unclear. Some scientists argue that the magma rivers could have been a temporary phenomenon, while others believe they might have persisted for millions of years. Without more data, it's difficult to say which scenario is more likely. This uncertainty highlights the importance of continued exploration. Missions to Mars, such as the Perseverance rover and future sample return missions, could provide critical insights into the planet's geological history. By analyzing rock samples and studying the planet's surface in greater detail, scientists may be able to confirm or refine the findings of the magma river study. However, even with these missions, the answers may not be straightforward. The geological record is often incomplete, and the processes that shaped Mars' past may have left few direct clues. This brings us back to the central challenge of planetary science: interpreting indirect evidence to reconstruct the history of a world that no longer exists in its original state. The study of magma rivers on Mars is a testament to the power of scientific inquiry, but it also serves as a reminder of the limits of our knowledge. While the research opens new avenues for understanding planetary habitability, it also underscores the need for humility in our interpretations. The search for life beyond Earth is a complex and multifaceted endeavor, and each discovery brings both excitement and new questions. As we continue to explore the mysteries of Mars and other planets, we are not just uncovering the past, we are redefining what we know about the potential for life in the universe. Now that we've uncovered the possibility of ancient magma rivers beneath Mars, the next step is to explore how we can confirm or expand on this discovery. Let's look at the missions and tools that will help us uncover more about Mars' hidden past and its implications for life beyond our planet. The search for evidence of these magma rivers isn't just about Mars, it's about understanding the broader story of rocky planets and their potential to harbor life. Future missions, cutting-edge instruments, and even observations from distant worlds will all play a role in shaping what we know. But first, let's consider what's already in motion. The Perseverance rover, currently exploring Jezero crater, has already provided critical data about Mars' geological history. Its instruments, like the scanning habitable environments with Raman and luminescence for organics and chemicals, Sherlock spectrometer, are designed to detect organic molecules and mineral signatures that hint at past water activity. While these tools haven't directly probed for magma, they could uncover indirect clues. For example, if ancient lava flows interacted with water, they might have left behind unique mineral deposits or isotopic signatures that Perseverance could identify. Similarly, the Mars 2020 mission's radar imager of Mars and subsurface experiment, RIMFAX, is already mapping subsurface layers, revealing structures that could resemble ancient magma channels. These findings, combined with data from previous rovers like Curiosity, are building a more detailed picture of Mars' geological evolution. But to truly confirm the existence of magma rivers, we need to dig deeper, both literally and metaphorically. Enter the Mars Sample Return Mission, a joint effort between NASA and ESA. Scheduled for the late 2020s, this mission will collect and transport samples from the Martian surface back to Earth for analysis. If any of these samples contain evidence of volcanic activity or high-temperature mineralization, it could provide direct proof of magma rivers. For instance, certain volcanic minerals, like olivine or pyroxene, form under extreme heat and pressure, conditions consistent with magma flow. By studying these minerals in a lab, scientists could determine their origin and whether they were shaped by rivers of molten rock. However, the journey of these samples back to Earth is a complex endeavor. The samples must be collected, sealed, and transported through the Martian atmosphere, a process that requires precise engineering and careful planning. Once they arrive, they'll be subjected to advanced analytical techniques, such as electron microscopy and mass spectrometry, to unlock their secrets. This mission represents a monumental leap in our ability to study Mars, but it's just one piece of the puzzle. To probe the planet's interior, we need to look beyond the surface. The InSight lander, which touched down in 2018, has already made groundbreaking discoveries by measuring seismic waves, Marsquakes, to map the planet's interior. Its Seismic Experiment for Interior Structure (SEIS) instrument detected vibrations that revealed the structure of Mars' crust, mantle, and core. While InSight hasn't directly observed magma rivers, its data could help scientists model the planet's thermal history. If Mars once had active magma channels, they might have influenced the planet's internal heat flow, leaving subtle traces in the seismic data. Future missions could build on this by deploying more advanced seismic sensors or even drilling into the crust to collect core samples. However, drilling on Mars is a significant challenge. The extreme temperatures, thin atmosphere, and rugged terrain make it a high-risk endeavor. Yet, the potential rewards are immense. A core sample from the Martian crust could reveal the composition of the planet's mantle, offering clues about its volcanic history and the presence of magma reservoirs. Such data would not only confirm or refute the magma river hypothesis but also provide insights into the geological processes that shaped Mars and other rocky planets. Beyond Mars, the search for magma rivers extends to our solar system and beyond. Venus, for example, is a planet of extremes, with surface temperatures hot enough to melt lead and a thick atmosphere of carbon dioxide. Despite its harsh environment, Venus is believed to have been more Earth-like billions of years ago, with oceans and a cooler climate. If Venus once had magma rivers, it could have played a role in its geological evolution. Future missions to Venus, such as NASA's proposed Venus Climate Mission or ESA's Envision, could use radar and spectrometry to study its surface and subsurface features. These missions might uncover evidence of ancient volcanic activity or magma channels, shedding light on how Venus transitioned from a potentially habitable world to its current state. Similarly, observations of exoplanets, planets outside our solar system, could provide further context. The James Webb Space Telescope and upcoming missions like the Plato Telescope, planetary transits and oscillations of stars, are already scanning distant worlds for signs of habitability. While these telescopes primarily search for atmospheric signatures of water or oxygen, they could also detect signs of volcanic activity. For instance, certain gases like sulfur dioxide or carbon monoxide might indicate ongoing volcanic processes. If such signals are found on an exoplanet, it could suggest that the planet has a dynamic interior capable of sustaining magma rivers or other geothermal activity. This would expand our understanding of where life might exist, as it would imply that even planets with different atmospheric conditions could support geological processes similar to those on Mars. However, the search for magma rivers isn't without challenges. One major hurdle is the difficulty of interpreting indirect evidence. For example, the presence of certain minerals or geological features could be explained by multiple processes, such as tectonic activity or meteorite impacts. To distinguish between these possibilities, scientists will need to combine data from multiple sources. Seismic data, mineralogical analysis, and remote sensing observations must all be considered together. Additionally, the assumption that magma rivers on Mars were similar to those on Earth may not hold. Mars has a different composition, lower gravity, and a different geological history, which could mean its magma rivers behaved differently. For instance, the viscosity of magma on Mars might have been higher or lower than on Earth, affecting how it flowed and where it pooled. Future studies will need to account for these variables, perhaps by comparing Mars to other planets with known volcanic activity, like Io, the most volcanically active body in the solar system. Io's magma rivers are driven by tidal heating from Jupiter's gravity, a process that might have been less intense on Mars. Understanding these differences could help refine models of magma flow on rocky planets. Another challenge is the timescale of these processes. The magma rivers on Mars, if they existed, would have been active billions of years ago, during a period when the planet was still geologically active. However, much of this history is buried beneath layers of dust, ice, and rock, making it difficult to reconstruct. Future missions could address this by targeting regions with preserved geological records. For example, the polar ice caps on Mars may have preserved ancient layers of rock and sediment that could contain evidence of past volcanic activity. Similarly, impact craters, which can act as natural drill holes, might expose deeper layers of the crust that reveal the planet's geological history. By studying these regions, scientists could piece together a timeline of Mars' volcanic and tectonic activity, including whether magma rivers played a role in shaping its surface. The implications of these findings extend far beyond Mars. If magma rivers were common on rocky planets, it could mean that many worlds in our galaxy have had the potential to support life. For instance, the presence of magma rivers might have contributed to maintaining liquid water beneath the surface, creating environments where microbial life could have thrived. This idea is already being explored in the search for life on Europa and Enceladus, where subsurface oceans are thought to be sustained by geothermal activity. If similar processes occurred on Mars, it could mean that the planet was a more hospitable place in its early history than previously thought. However, the discovery of magma rivers also raises new questions. For example, how did these rivers form? What triggered their movement? And how long did they last? The answers to these questions could provide insights into the broader mechanisms that drive geological activity on rocky planets. One possibility is that Mars' early history was marked by intense volcanic activity, driven by the planet's internal heat. As the planet cooled over time, this activity diminished, leaving behind the remnants we see today. But if magma rivers were a significant part of this process, their existence would have influenced the planet's climate, atmosphere, and even its magnetic field. Understanding these connections could help us better model the evolution of Mars and other planets. In the coming years, the quest to uncover the truth about Mars' magma rivers will involve a combination of robotic exploration, advanced instrumentation, and international collaboration. Each new piece of data will bring us closer to a comprehensive understanding of the planet's past and its potential to support life. As we look to the future, the search for magma rivers is not just about Mars. It's about expanding our knowledge of the universe and the conditions that make a planet capable of sustaining life. Whether through the samples brought back by Mars Sample Return, the seismic data from future landers, or the observations of exoplanets, the next chapter in this story is just beginning. And as we continue to explore, we may find that the answers to some of the most profound questions about our place in the cosmos are hidden beneath the surface of worlds we've yet to fully understand. So, what did we just uncover about Mars? Let me break it down. First, researchers have found compelling evidence that ancient rivers of magma once flowed beneath the Martian crust. This isn't just a trickle of molten rock, it's a vast, dynamic system that suggests Mars was geologically active in ways we didn't fully expect. Second, this discovery reshapes our understanding of planetary habitability. For decades, scientists have focused on liquid water as the key to life, but now it seems volcanic activity might play an equally critical role. Mars, once thought to be a cold and barren world, could have harbored conditions capable of supporting life far longer than previously imagined. Third, this finding doesn't just apply to Mars, it points to a broader truth about rocky planets. If Mars, with its thin atmosphere and extreme environment, could sustain magma rivers in possibly habitable conditions, then other exoplanets in similar circumstances might too. It's a reminder that the universe is full of surprises, and our search for life beyond Earth just got a lot more exciting. But how did this discovery come about? Let's rewind. The clues started with seismic data from NASA's InSight lander, which detected quakes that hinted at a layered interior. Then, by analyzing the planet's topography and mineral composition, scientists noticed patterns that align with volcanic activity on Earth. They modeled how magma could have carved channels through the crust, much like rivers shape landscapes. But here's the twist: unlike Earth's plate tectonics, Mars' magma rivers might have operated under different rules. The planet's smaller size and cooler interior could have allowed these rivers to persist for billions of years, creating a stable environment for chemical processes that might have nurtured early life. This isn't just about Mars, it's about rethinking what makes a planet habitable. For years, we've assumed liquid water was non-negotiable, but if Mars shows us that volcanic heat and subsurface chemistry can create life-sustaining conditions, then our criteria for habitable worlds just expanded. Imagine other rocky planets with similar geological histories. Maybe they've got their own hidden oceans, or maybe their magma rivers are still active today. The implications are staggering. But let's not get ahead of ourselves. This research is still in its early stages. Scientists are still debating the exact mechanisms that allowed these magma rivers to form and how long they lasted. Some wonder if they were short-lived bursts of activity, while others argue they could have been steady flows for millions of years. And then there's the question of whether these conditions were enough to support life as we know it, or if they point to entirely new forms of biology. What's clear is that Mars isn't the cold, dead rock we once thought. It's a world with a complex geological past, and its story could hold answers to some of the biggest questions in science. So, what does this mean for us? Well, it means we need to look beyond Earth's familiar patterns. When we search for life in the cosmos, we might need to consider planets that don't have oceans but have active volcanoes, or worlds that never had liquid water but had persistent heat sources. It's a shift in perspective that could redefine our search for extraterrestrial life. And that's just the beginning. This discovery is part of a larger trend in planetary science, one that's challenging our assumptions and opening up new possibilities. But to keep exploring these ideas, we need your support. If you enjoyed this deep dive, hit that subscribe button and turn on notifications so you never miss the next episode. And if you've got questions or theories about Mars magma rivers or the search for life beyond Earth, drop them in the comments. The universe is full of mysteries, and together, we're just beginning to uncover them.